Hey, it's Mr. Saltano. This video is going to be on chemical reactions versus nuclear reactions. So, remember that we said the most important particle for regular chemical reactions was the electron. So here's our quick review, rehash of atomic structure. Remember that there is the nucleus that contains the protons and neutrons, and then there's the electrons on the outside of there. We said the electron was the most important part for chemical reactions, and that's because remember in a chemical reaction you're having old bonds break and new bonds form, right? So what makes up bonds? It's the electrons. So that's all that's happening in a reaction is we're breaking old bonds, making new bonds, all the electron. So then which part of the atom do you think nuclear chemistry involves? So that does involve the nucleus, right? Just this center part of the atom. So I think when people hear about nuclear, they tend to think about like huge nuclear bombs, nuclear explosions, nuclear waste, things like that, and kind of not make the connection that nuclear is because of the nucleus. That's why it's called that. It has to do with just the center of the atom here. So really just the protons and the neutrons is what it has to do with. No more electrons are going to be part of it overall. So, like I said in the past, we've talked about electrons being shared, right? That was a covalent bond in a regular chemical reaction. And also there was ionic bond that had loss and gain of electrons, right? So that was also in a regular chemical reaction. Something else that we said happens, we just got finished doing the balancing, right? So in a regular chemical reaction, we were trying to get the same number of each atom on both sides, right? So on the left and the right side. So for example, there's 4 hydrogen atoms on the left here. There have to be 4 hydrogen atoms on the right. So the same elements would appear on both sides of the equation, and the same quantity of each type of atom would be there on both sides, right? Those were the rules. And also because of that, that meant the mass on both sides would be equal as well. So before the reaction, if you took the mass, it would be certain mass, just like we see here. And then after the reaction, if you took the mass, it would be the same mass, just new chemicals, right? Old bonds broken, new bonds formed. This was in a regular chemical reaction. In a nuclear reaction, it's a whole different story. So remember that we said that for a chemical's identity, in order to decide what type of element it is, we look specifically at the proton number. That was like the social security number of the element, and that was the most important one. Regardless of how many neutrons it had, regardless of how many electrons it had, the proton told you who it was. So because of that proton number tells you the identity of the element, that means that we're going to have something entirely different in nuclear because we're changing the nucleus. We're affecting the nucleus now. So the identity of each particle will change. So here's an example. We're looking at uranium, which has an atomic number of 92, right? So this is before the reaction. There's a neutron being fired at it. That causes the nucleus of the uranium to actually split. So that's what you see that's happening here. It's unstable. It's starting to actually split the nucleus. This is what we say when we mean we're splitting the atom, right? You've probably heard that term before. And if we look at it, we had atomic number 92, right? Uranium 92, 92 protons total. It's splitting into a particle that has 36 protons. Now, because that particle has 36 protons, that means that we can know it's krypton. If we were to check the periodic table, krypton has 36. That's its atomic number, 36. So that means that this nucleus here must belong to a krypton atom. At the same time, this nucleus has 56 protons in it, so that means it must be a barium nucleus. And if we look, 56 plus 36 is going to add up to our 92. So what happened was we started with a certain element, in this case uranium, and it split into krypton and barium, and that's why we actually have a whole different element than what we started with. So if we look at the regular chemical reactions, same elements on both sides that we're trying to get to, same mass. In nuclear reactions, we start with one element, certain types of elements, and in the end we have an entirely different element because we're actually changing the proton number, which is in the nucleus. Even if you look over here, here's sort of our beginning stages. This is the part that's right here when that neutron's been added to the nucleus. And then here's the part after the reaction. We had uranium, now we have barium, krypton, and some neutrons. So start with one type of element, have entirely different elements. So it's a whole different thing from regular reactions in that regard. We're transmuting into entirely different things. Something else that we'll talk about in the future is that in a chemical reaction, we expected the mass to stay relatively the same. Pretty much the same. We could account for all of it. Remember, matter can't be created or destroyed, only rearranged. So the mass before and after was the same. But for a nuclear reaction, we're actually going to see a change in mass. Even though we'll have all the particles accounted for, some of that mass actually gets converted to energy in a nuclear reaction. And it only takes a little bit of mass to get a huge, enormous amount of energy, which we'll talk about in a second. But so the mass will actually change over the course of a nuclear reaction. The other thing is, when we had our regular chemical reactions, some of them would give off heat, right? Some of them would involve little bits of energy to produce heat as a result of the reaction. You may remember that those are called exothermic reactions, right? If they're giving off heat like that. So here's an example of an exothermic reaction. In a nuclear reaction, they're giving off enormous, orders of magnitude larger amounts of energy. Huge, huge difference there in a nuclear reaction. And that's because, like we said, some of that mass is actually getting converted into energy. But much, much different. The nucleus has a lot more pent-up energy available as opposed to just the energy being released as a result of electrons from chemical reactions. So nuclear reactions, much, much more energy. So here's our quick summary. We're pretty much all set. Chemical reactions depend upon only the electrons and bonds. That was all that mattered for those. Nuclear reactions depend only on the nucleus, which is the protons and neutrons. Chemical bonds are not involved in nuclear reactions. In chemical reactions, we expect the same types and the same numbers of atoms to exist on both sides of the equation. If we've got 4 hydrogen and 2 oxygen on one side of the equation, we would expect 4 hydrogen and 2 oxygen on the other side, maybe just different bonds, essentially. And we also would have, for chemical reactions, the total mass before and after wouldn't change. Conservation of mass, right? Same mass before, same mass after. In a nuclear reaction, we don't have the same elements on both sides. We actually made entirely new elements. And also there are some changes in mass that occur over the course of the reaction. And then finally, in a chemical reaction, relatively small amounts of energy compared to the enormous amounts of energy that come in nuclear reactions that make our nuclear bombs and nuclear power. The sun itself is one giant nuclear reaction that's been going on for years that provides just unimaginable amounts of energy. So that's it for the differences between chemical reactions and nuclear reactions. Thanks for watching. Remember, chemistry is everywhere.